Okay, so welcome to the second part. We stated the sampling lemma. Now we need to prove it, and the proof is actually quite simple and elegant. So let H be a random inequality from H minus R. Okay, so it's easy to see. Just think about it for a minute. That the expected number of violated inequalities actually n minus r times the probability that a random inequality is violated. A random inequality which is not in R is violated. So of course the inequalities in R are not violated. The only inequalities that can be violated are inequalities of H minus R. And if we choose such a random inequality, compute the probability of this event and multiply it by n minus r, we get the expected number of violated inequalities. So everything we need to do, all we need to do is to evaluate this probability. Okay, and here comes a nice trick, which makes the computation simple. So instead of choosing a subset uppercase R of size R and an inequality not in R, let's begin by choosing a random subset R prime of size R plus 1. And then from this set, we'll choose a random inequality. Okay, and let H prime be a random inequality from R prime. Now, what can we say about the distribution of uppercase R and H and R prime and H prime? What can you say about the relation? It's exactly the same distribution, right? It doesn't really matter in which order we did it. Okay? So instead of computing the probability that V of R violate H, we need to see what's the probability that this happens. Okay, what's the probability that if we take a random inequality H prime from R prime and delete it, then the solution that we get violates H prime. Now, when can this happen? Only if H prime is part of the basis of VR prime. Right? What's the size of the basis? D. Right, so what's the probability that this happens? It's exactly D over R plus 1. Okay, so that's the probability that we get a violation. We just need to multiply it by an A minus R, and we get this bound. Okay, so we don't have too much time to dwell on it because there are many things I still want to cover, but just go over this if you're interested. Go over this proof slowly. After the talk, you'll see that every step here is fairly trivial, and we get this upper bound. And by the way, this is an example of what is called backward analysis in computational geometry. It's a very neat technique. Okay, so we get this upper bound. Now, intuitively, it just says that we choose a random inequality out of a set of R plus 1 inequalities. The probability that it's essential is exactly this. It's D over R plus 1. That's the probability that a random inequality is violated. We multiply it by the number of potentially violated inequalities. We get this upper bound. Okay. Okay, so here's the analysis of Clarkson's second algorithm. Here is the key claim. Okay, so let B be a basis of the solution. Okay, now, and as part of the annoyances, I view B as unique. Okay, there are some cases in which the optimal basis is not unique. We discussed that we break ties somehow, but let's forget about this thing. So B is a fixed basis. And I claim the following. So let's look at the total weight of all the inequalities in the bases after KD successful iterations. Remember, a successful iteration is an iteration in which not too many of the constraints are violated. And I claim the following. I claim that after KD successful iterations, if there were KD successful iterations. Eventually, the algorithm terminates, and then there are not so many iterations. But if the algorithm did perform at least KD successful iterations, then we have the following bounds on the total weight of B. It's at least 2 to the k, and it's at most n times e to the k over 3. Okay? So we'll prove this lemma, and we'll see why this solves all our problems. Okay, so let's look at the lower bound first. It's both directions are actually easy. So in each iteration, if this is not the last iteration, at least one of the inequalities in the bases is violated, right? Because if all the inequalities of the bases are satisfied, we are done. We found a solution. So in each iteration, so if it's not the last iteration, at least one of the D inequalities in the basis B is violated. And if it's a successful iteration, the weight of this inequality will be multiplied by 2. Right? Now, if we have KD successful iterations, then in KD successful iterations, at least one of the D inequalities had its weight doubled at least k times. Okay, that's why we have the following claim. Okay, and in fact, this lower bound is not tight. We can actually improve it slightly, but we don't need to. Okay, what about the upper bound? So, in a successful iteration, the total weight is increased only by this factor. Okay, because we were in a condition in which the total weight of the violated inequalities was at most the total weight over 3D. So that once we do the doubling, the total weight of all the inequalities is multiplied by at most 1 plus 3 over D. Therefore, in KD successful iteration, the total weight started to being n, because each inequality had weight 1. And we multiplied it by at most 1 plus 3 over D, KD times. Okay, now we have the standard inequality that 1 plus 1 over D to the D is less than E. Okay, and since we have a 3 here, we get the following bound. Okay, so that's the whole proof of this lemma. By the way, so I mentioned the backward analysis, which is really an interesting technique. This is just a nice example. This is also a nice example of something called multiplicative weight updates, which is used everywhere now. You can find it in many sophisticated algorithms. This is again a very nice example. Okay, so this is what we proved. Now, if you look at it for a second, you might be a bit worried. Why? Because if k is large enough, then this is actually larger than this. Because if you look at what is e to the 1/3, it's actually less than 2. Okay, so is this a cause of worry? That's great. That actually means that k cannot be too large, right? This is exactly what we need, right? So if we, from this inequality, we get the following inequality, which actually implies that k is at most 2 log n. Okay, so that's great. So we know that overall the algorithm can perform at most 2D log n successful iterations. Okay, but now what about the unsuccessful iterations? Maybe there are a lot of them. Okay, but note that by the sampling lemma we have the following bound on the expected number of violated inequalities. So if an iteration is not successful, then the number of violated inequalities is larger than twice the expected number. Okay, and then by Markov's inequality, we know that this happens with probability which is less than 1/2. Okay, so on average, every second iteration is successful. Therefore, the total number of iterations we need until getting KD iterations is order KD. In fact, it's at most 2 KD. Therefore, the expected number of iterations is at most 4D log n. Okay, and this is essentially the end of the proof, because in each how much work did we do in each iteration? We did one call to the base algorithm. That's the complexity. And what else did we do? We just took the solution returned by this base algorithm, just checked each inequality, whether it's satisfied or not, and this is just can be easily done in order dn time. Okay, so we take this multiplied by the bound on the number of iterations, and we get exactly the bound I claimed, which is this. Okay, questions on this? So this, if you remember, this is the second algorithm of Clarkson. There is the first one, which is similar. We will not cover it, but okay. So the next topic on the agenda is the improving Zeidel's algorithm, and this was obtained by Matoušek-Sharir-Welzl. So in 1992, and this algorithm I'll actually call dual random facet. Dual because it's actually working, it's a simplex algorithm working on the dual problem, as I mentioned. Random facet, we'll see in a minute what this is. So this algorithm was came after Zeidel's algorithm, and it's an attempt to improve Zeidel's algorithm. Well, it's actually a successful attempt to improve Zeidel's algorithm. And the main point, the starting point is the following. Remember Zeidel's algorithm, right? So we eliminated inequality. We did a recursive call. We found a solution. If this solution was, if this solution violated the inequality we neglected, okay, so we used that inequality, so we turned that inequality into equality, and we recursed, right? But the only thing we got from the first recursive call is that single inequality. Now, the main point of Matoušek-Sharir-Welzl is that actually the first recursive call gives us much more also gives us a lot of information about the second problem we want to solve. And just forgetting about everything that happened in the first recursive call is very, very wasteful. Okay? So even though it was essentially solving the wrong problem because it didn't have one of the important inequalities, there are still a lot of useful information that we can gain from that first recursive call, which would make the second recursive call much more efficient. In fact, much more efficient than they imagined in the beginning. Okay, and the way to capture this information, that additional information that we can get from the first recursive call, is to explicitly work with bases, not just with solution. Let's see how this is done. So the MSW algorithm, so again, the input is a set of inequalities, but now, like a good simplex algorithm, there's also an initial base. Initial base is B. Okay. Now, this initial basis doesn't have to be optimal. Of course, if it's optimal, we've solved the problem. But it is some basis, and it gives us some upper bound on the value of the problem. Okay. Now, and the goal of the algorithm is to find the optimal solution and a corresponding basis. Now, note that the initial base doesn't. So no matter which initial base we start with, we always get the same solution, but the quality of the initial base has a large influence on the running time of the algorithm. Okay, and the main point is that we would start with the second recursive call using a base that we obtained from the first recursive call, and hopefully this would be a good starting point for the second recursive call. Okay, so here's the algorithm. Okay, like Zeidel's algorithm, we choose a random inequality, and we will remove it. But the important thing is that we only choose an inequality which is not currently in the basis. Okay, so the basis that we have at each time, we are not sure, so it's not the optimal basis, but we think it has some useful information in the sense that we hope that at least some of the inequalities in the current basis, we hope that many of them are actually essential. So we don't want to remove an inequality from the basis. We choose a random inequality not in the basis, and we remove it. So we do a recursive call on h minus h, now using the same basis that we have. Okay, and as a result, we get a pair, an optimal solution, and the basis for this subproblem. Okay, now if the solution we got, the vertex we got, satisfies h, then we are done. This is also the solution of the whole problem, so we just return the pair v prime, b prime. Okay? Otherwise, what do we do? So what did Seidel do? Seidel took this inequality and turned it into an equality. So we can also do it here, but we don't do it explicitly. We're sort of doing implicitly in the sense that we insert it into the basis. Okay, and in this case, we actually know that once we insert this inequality into the basis, we'll see it would never leave the basis. So it's as if we turned it into an equality. So more specifically, we introduce the following operation, which I have to define, right? So b prime is the basis returned by the first recursive call. Okay. Now, what do we know? What do we know about the relation between h and b prime? So b prime determines v prime, right? And v prime violates h, right? So what we want to do now is we essentially look at a tiny linear programming problem composed only of these d+1 inequalities, and we find the optimal basis of that solution, of that small subproblem. Now, what that would mean is that h would enter the basis, and one inequality from b prime would exit the basis. Okay? And as a result, we'll get a better basis. Better in the sense that, better in the sense that the value of this basis would be smaller. Right? Now, remember that we are maximizing. The original problem is maximizing, but we have a dual algorithm. So what we have is essentially we always have infeasible solutions, but the value of these infeasible solutions are dropping until we get a feasible solution. Then it's the optimal solution. Okay, but the important thing here. Okay, and once we have this new basis b prime, we do again a recursive call with all the inequalities, but now starting with the basis b prime. Okay? Now, exactly what I said now, note that b prime is a better basis than b, in the sense that v of b prime is less than v of b. Now, here I actually introduce another notation. What do I mean by v of b greater than v of b prime? I mean the objective function at this vertex. Okay, so think about it as we think about it just as the height, right? So this is lower than this. And this is why we make progress. And this is why the algorithm must terminate. No matter what random choices we made, eventually the algorithm will terminate. Because if the solution we got from the first recursive call is not really the optimum, then we actually so note that the second recursive call might look a bit frightening, because we work with exactly the same set of inequalities. So it's not clear why we are making progress. Why can't we cycle? The progress is made because b prime is a better basis. Okay, so that's the whole algorithm. Now, if you look at it, you may think that it's not such a big deal, right? So I'll show you in a minute that once we do this step, H enters the basis B prime, B double prime, and it will never leave it. It's essentially like imposing this inequality with an inequality, and this is also done by Zeidel's algorithm. So why is this much better? What we'll see in a minute is that with good probability, when we do this, note that that the first recursive call returned the basis B prime, okay, which might be quite different than the basis B that we started with. And the claim would be that with high probability, B prime would already include some of the essential inequalities, even though we didn't work on the right problem. Okay, so when we do the second recursive call, the hope is that we didn't decrease the dimension just by 1. We hopefully decrease the dimension by more than 1. But here is the neat thing is that we don't know by how much we decrease the dimension. And the other neat thing is that it doesn't matter. The algorithm would use that. Okay, we'll see the exact details. Okay, so that's now we get to the analysis of the algorithm, and this is more involved than everything we saw. We'll probably spend some 10 minutes on this analysis, and there are some intricate details, so it's really a nice analysis. And I should, to be fair, I should actually say that, so Matoušek-Sharir-Welzl came up with this algorithm in 1992, and they showed that it improved Zeidel's, but they didn't quite know how to get a tight analysis of their algorithm. And independently, around the same time, Gil Kalai had a primal version of the simplex algorithm, and he proved that his algorithm is sub-exponential. And once Matoušek-Sharir-Welzl saw that analysis, they said, this can also be applied in our case. So essentially what I'm doing now should be attributed both to Gil Kalai and Matoušek-Sharir-Welzl, and later it was actually observed that the two algorithms are actually identical, except that one is working on the primal problem, the other one is working on the dual problem. Okay, so here's the analysis. So we have n inequalities, so let's number them, h1, h2, up to hn, but in the following way. Okay, so we take each inequality individually, remove it from H, and see what is the optimal solution. Okay, and we sort it in a non-increasing order. Now, note that we might as well take the first D inequalities in this order to be the basis of the optimal vertex. And then the nice thing is that once we remove an item which is not in the basis, we get exactly the optimal basis. Okay, so it's a fairly boring line of inequalities because all these inequalities are actually equalities. Okay, and these are inequalities. Now, note that if this is the only basis, then this is actually a strict inequality. But for a change, I'm not even assuming that. Okay, so everything actually works if it's not a unique basis. I just don't want to explain what happens. So let's assume that this basis is actually unique. So there's a unique set of D essential inequalities, H1 up to HD. Okay, so what does this order mean? Okay, so H1 up to HD, they are all essential, but which one of them do we view as the most essential? So note that H1, so of course there might be equalities here, but H1 is one of the most essential inequalities, right? Because if we forget about H1, we get the largest result of all the other results. Eventually we want to get here. Okay, so it sort of gives an order to these not a strict order, because there might be many inequalities here. I don't claim that all these are inequalities, but sort of H1 is sort of more important than H2, more important than HD, and so on. Okay. Now, one trivial observation. The algorithm chooses a random inequality which is not in the basis. If it happens to be one of the last n minus d inequalities, then we are very happy, because there would be no second recursive call, because we removed a non-essential inequality, right? So the only danger is that if the algorithm chose one of these d essential inequalities, one of the d inequalities in the optimal basis, okay? And we already know that this probability is at most d over n, but we want to get a much stronger analysis. So let's now focus only on these d inequalities. So I'm enlarging this this d or d minus 1 inequalities, and I want to see where does v of b being our current basis, falls in this line of inequalities. Okay? And I let k be the unique index in which the following happens. Okay, now note that so I look at the maximal number of items here which are strictly larger than v of b. Now, how do I know that there is at least one of them? I don't know. So k might be d, in which case vb is actually greater or equal to this. Okay, but k is uniquely defined, and it's between 0 and d. Okay, so this is an index k, which turns out to really be essential. We'll see in a minute why. Now, what can we say about the relation of b and these inequalities h1, h2 up to h d minus k? Any idea? No, so they are in the solution. This is how we define them. But they must be in B, right? Because if they were not in B, then VB would not be smaller than all these. So these inequalities, H1, H2 up to HD minus K, must be in our current basis B. Okay, because, for example, if we didn't have H1, then the optimal solution is this vertex, and B would be a subset of H minus H1. And so since it's a maximization problem, VB would be greater than, at least as large as VH minus H1. So it means that H1 must be currently in our basis. And similarly, H2 up to HD minus K. Okay, now what happens with all the other, all these K inequalities? We don't know. They might be in B, they might not be in B. Okay, now K is really the cornerstone of this argument. We call it the hidden dimension. Now, what is the interpretation of K? It means that we have D minus K constraints from the correct basis, from the optimal basis, which are currently in our basis. Okay? We don't know who they are, but they sit there. And I claim that they would never trouble us again, in the sense that they would never leave the basis. Okay? Why wouldn't they never leave the basis? Because we keep moving from a base to a better base. So VB would always decrease. So these inequalities would always be maintained, and this applies that all these inequalities would actually remain in our basis. Okay? So note that what that means is that if the hidden dimension is k, we're essentially working on a d-dimensional. So we think we are working on a d-dimensional problem, but in fact we are working on a k-dimensional problem. We don't know which problem it is, but it's hidden somewhere in our computation. Okay. Now, a second recursive call is made only if the random inequality H that we choose is a member of these k inequalities. Okay, now let's see what happens if we do choose one of these inequalities. This is just a recap of what we said in the last slide. Okay, here's the punchline. Okay, now I hope I'll be able to explain it clearly. Okay, so the only case in which we have a second recursive call is in if H is an item of this set. Okay? Now, if it is an item of this set, it's a random item of this set. Now, let's see what happens if we choose the ice inequality among this set. Right? This is a set of size k. Suppose we chose the ice item of this subset, so little h is h d minus k plus 1. Okay, what happens? So the first recursive call returns a basis b prime, such that v of b prime is exactly v of h, ignoring this inequality. Okay, now, if it's if this is not the solution of the original problem, we know that the solution that we got does not satisfy the inequality that we removed. And what does the algorithm do next? It does this basis change, right, and computes b double prime. But what do we know in that case? In that case, we know that b double prime is actually strictly better than vb prime. Okay, so what does that mean? What happened to the hidden dimension, defined, if you remember, according to this list of inequalities? So now, we're actually, VB is not just smaller from all these values, it's actually smaller from the corresponding value at index d minus k plus I. In other words, the hidden dimension decreased from k to k minus I. Okay, so it might be, I understand it's a challenge to grasp this proof, I mean, on the fly when you see it in a talk, but I hope I essentially said all the details, right? So this is just to give you an impression that the proof is simple. I mean, you just have to look at and what is going on, and really it follows from the basic definitions. Now, let's see what are suppose that you believe me, and so the claim we just need to take from this is that when there is a second recursive call, if before the second recursive call the hidden dimension was k, after the second recursive call, the hidden dimension is k minus I. And how is I distributed? It's uniformly distributed between 1 and k, right? So this is okay, again, comparing it to Seidel. In Seidel, the second recursive call, we got a big saving because instead of working in dimension d, we work in dimension d minus 1. But here, not that k is always at most d. So the second recursive call is in a dimension which is randomly distributed between 1 and d. So this is really a huge saving, right? Now, if we write it explicitly, we get the following recurrence relation. Okay, let me, so, and the nice thing here is that the running time here is expressed in terms of this parameter k, which is the hidden dimension, which the algorithm doesn't know. Note that all this analysis is oblivious to the algorithm, right? So the algorithm doesn't know what is the current hidden dimension. But it doesn't matter. The algorithm just chooses a random inequality which is not in the basis, and the only bad case is in which this inequality falls in this subset, and even in that case, we are likely to get a big decrease in the hidden dimension. Okay, so that's the first recursive call. The only thing that happened is that we have one less inequality. And now, note that, what is this? So we choose a random inequality from which is not in the basis. So there is n minus d choices. And we average over all these choices because each one of them was chosen with the same probability. Now, the only case in which we actually hit something which would result in a second call is in which, so the number of choices that would result in a second call is actually at most the minimum of k and n minus d. Okay, so, so n minus d is clearly an upper bound, and k is exactly this set. Only in this case we have a second recursive call, and if this happens, then I is just uniform in this range, and we get a recursive call in which the hidden dimension is actually k minus I. Now, what is this one? So in this recurrence relation, I'm actually counting basis changes. This would be my currency. Now, and a basis change is polynomial. It's something like d squared. So I factor that out of the calculation. So this is this basis change. Okay, so we get this strange-looking recurrence relation, and we have these bounds on these parameters. And this is actually now quite a complicated process, showing that we can actually get the following upper bound on this recurrence relation. And the nice thing here is that this is sub-exponential in d. Right? It's roughly 2 to the order root d, or if you like, root of d log n. Okay. And note that since we are going to apply Clark's algorithm, we don't really care what happens when n is huge. We only care what happens when n is at most 6d squared, and then we get this term, okay, which is what I promised you in the beginning. So I gave you all the details except the analysis of this recurrence relation, and it's actually, in a sense, it's possible to prove it by induction, but it's once you know the exact bound, but yeah, it's of course it's not. The original analysis was using generating function, and it's quite involved. Okay. So I'm not going to give you the analysis, the analysis of this recurrence relation. I just want to give you a sort of an intuition where this sub-exponential behavior comes from. So let's look at a much simpler situation in which we have just a one-dimensional recurrence relation. Okay. Now I said that sort of in each iteration the hidden dimension is, on average, drops down by a factor of 2. Now, suppose that this happened all the time. We would get something. We would get a recurrence relation which is sort of something like the following, right? Actually, add here 1, just to make it more precise, but yeah, or you can just say that f of 0 is 1. But so this is the first recursive call in which we just decrease the size by 1, and a second recursive call in which we are likely to halve the size of the problem. Okay, have you seen such a recurrence relation before? Yes? Where did you see it? Hmm? Well, tell me after the...
Some quasi-polynomials. Lots of quasi-polynomials.
The what?
Lots of quasi-polynomials.
I see. Okay. So what's the solution? Yeah, so the solution here is n to the log n. Now, note that this is much better than what we claimed, right? We got sub-exponential. Now, why is that? So it's true that on average, that the hidden degree dropped by a factor of 2, but in fact, it was uniformly distributed between 1 and n minus 1, and when it was large, we spent much more time than when it was smaller. So it's not a fair assumption to say that it's just dropped by 2 each iteration. So this is this is actually the accurate thing to say. So it's sort of an average of fi, where I goes from 1 to n minus 1. And the solution of this is sub-exponential. Now, this is, if you have enough, a rich enough imagination, it's reminiscent of this inequality, and this sort of indicates why we get this sub-exponential behavior. Okay? Okay. Very quickly, I'll give you what is. I'll say what is the primal version of the algorithm, and then I'll move to some concluding discussion. I'll mention some things. So we'll not do that in great detail. Just to give you a flavor. What happens if you really want a genuine simplex algorithm that works on the primal problem? How would that look like? So here's the algorithm. So we are at a given vertex of the polytope. This vertex is defined by k. This vertex is on the intersection of d facets. Okay. So what we do now is we choose at random one of these d facets, and what do? We cannot remove it, right? If we remove it, we'll get out of we might get out of the feasibility region. But this is the dual point of view. We now say, let's stay on this facet, okay, for the time being. So now we stay on this facet. That means that we are now in a d minus 1 dimensional problem, and we find the optimum subject to the assumption that this inequality that corresponding to the facet is actually satisfied with equality. Okay? Now, not the duality. Here we choose a random inequality and we make it random inequality in the basis and make it an equality. Now we solve recursively, and now there are two cases. Either the vertex we got to is also the top vertex of the whole polytope, in which we are very happy. Otherwise, we know that our assumption that we should stay on that facet it was the wrong assumption. We should leave that facet. And if you think about it for a second, you'll see that there is a unique edge from that vertex that leaves that facet. That's the pivoting step that we should do. We do that pivoting step, and what now? We just recurse. We run exactly the same algorithm again, but from the vertex we got to. Now, if we unravel the recursion, we exactly get a pivoting algorithm. We just move from vertex to vertex to vertex, and a similar analysis applies to this algorithm. With the so you can take the recurrence relations that I wrote and the solution, just replace d by n minus d. And everything would stay the same. Yeah, so that's the recurrence relation. In fact, I sort of prefer this view. I think it's easier to argue. but since, or maybe because I'm more used to it, but yeah, since the previous thing we did were more natural to consider them the dual setting, I decided to start with the dual setting. But okay, and the nice thing here is that we also have a hidden parameter here. So in the dual setting, we had the actual dimension was hidden. Here, what is hidden is the number of inequalities. This might sound a bit strange. Okay, so we have a set of n inequalities. Of course, the original set is given to us, but we actually know that there is a set that only n of them can actually matter. All the others are really not important. Of course, we don't know which inequality is not important, but if we hit one of the, okay, and note that what are the inequalities that really matter? These are only inequalities that may appear in vertices that we will encounter during our walk on the polyhedron. And we'll actually have a bound on the number of facets we would be able to hit. We don't know which these facets are, but in the analysis we can use this bound. Okay, don't think I have time for that. Also, so the interesting thing is that these algorithms, so the primal version and dual version were essentially discovered independently at about the same time, the same year, which is quite remarkable, even though the motivation for deriving these algorithms came from completely different directions. So we saw that Matoušek-Sharir-Welzl, all they were doing was trying to improve Zeidel's algorithm, and Gil Kalai started by getting an upper bound in the diameter, which he turned into an algorithm. And surprisingly, it's the same algorithm. Okay, so something like 5 minutes with some, to give you a sort of non-technical explanation of what's the meaning of all this, what we did, why is it interesting, maybe not, and okay. So, as I mentioned, there are actually polynomial time algorithms for LP, right? So there's an ellipsoid algorithm, there are interior point algorithms. Okay, so why do everything we did here, right? If everything is polynomial, right? So the thing is that while there are polynomial time algorithms, they are not known to be strongly polynomial. Strongly polynomial meaning that so the running time of these algorithms depend on the number of inequalities, the number of variables, and the bit size of all the coefficients in all these inequalities. Okay, it's not known whether there is an algorithm which is strongly polynomial, meaning that it would only depend on n and d. Now, what we were doing is, so if you can view it as an approach to try to get a strongly polynomial time algorithm, because everything we did, all the basic operations, were strongly polynomial. Everything we did was solving a system of linear equations, eliminating one variable. This is the number of arithmetic operations that we did was clearly, in each iteration, was clearly polynomial. So if we can get a polynomial bound on the number of steps, we would get a strongly polynomial time algorithm. So that would be an amazing result. Okay, the pivoting rules I described are more specifically random facet, are essentially the fastest known variants of the simplex algorithm. There are small improvements which I won't have time to explain, but they are sort of the best strong bounds. So right now we don't have a strongly polynomial time algorithm, we have a strongly sub-exponential algorithms for linear programming. And another advantage of this algorithm is that it's essentially the fastest known when the dimension d is small. For example, problems that arise in computational geometry where d is constant, this is much faster than throwing in interior point methods. Okay, one thing that natural to ask, I gave you an upper bound on the running time of random facet. And by random facet, I now call both the primal and the dual view, which are essentially the same. And as I mentioned, we sort of followed an abstract approach, right? So if you, this would be one of the next points. We didn't really rely on the geometry. We only relied on some abstract properties satisfied by vertices of polytopes. So the analysis we did was sort of, well, was clever, but was sort of very high level. We didn't actually use the geometry. So there was hope that maybe if we now do a more proper analysis, we'll actually be able to improve the upper bounds that we get. So unfortunately, this is actually now known not to be true. So the analysis that we presented is essentially tight. I mean, there is also so there are non-polynomial lower bounds. Essentially, there are bounds which are of a sub-exponential nature. So if we want to get a variant of the simplex algorithm which is polynomial, we would have to think of something new. Okay, one thing I mentioned several times is that random facet can solve a wider class of problems, and these wider classes go by different names. They are sometimes called LP-type problems. They are also known as abstract optimization problems. They are sometimes called the acyclic unique sync orientations. In each one of them, we can actually use variants of random facet. And in these settings, once we leave the world of linear programming, this is the fastest known algorithm. So without any, we don't have to make excuses, right? This is there are certain problems for which the algorithms I described are actually the fastest ones. Okay, finally, note that there's one basic obstacle to obtaining a polynomial simplex algorithm, which is the following. So the simplex algorithm starts at some vertex, and then it follows a path until it gets to the top vertex, right? So if we want this path to be of polynomial size, we might as well start by proving that there is a path of polynomial length, right? Forget even now about the problem of finding such a path. We don't even know that, currently we don't even know that there is a path of polynomial length. Now, note that this is essentially what is called the diameter. What is the maximum shortest distance of two vertices on a polytope? Okay, so this is really a major combinatorial OPE problem. So it's widely conjectured, widely believed that the diameter should be polynomial in N and D, but no proof is known. And the best upper bound on the diameter is currently N minus D to the log D. This is sort of a quasi-polynomial, and this essentially arises from the first strange recurrence relation that we saw.